Okay, welcome to our new unit on volumes. We're going to begin with a lesson on prisms, and this is going to include a quick review of some areas. Some of this will be a review, and some of this will or some of it will be new to you. Okay, and so what we're going to do is I'm going to start off by just showing you this table of area formulas, and the table of area formulas, of course, as usual, will be given on your theorem sheet, and all I'm going to do is just highlight a couple of key features of each of these formulas, and like I said, some of these you've seen before and you've worked with before, others will be relatively new to you. So the first is the area formula for a parallelogram, and that of course includes a rectangle, a square, and a rhombus, because each of these are parallelograms. The formula very simply is base times height. Of course, in the case of a square, we usually just do side times side, but given that in a square all four angles are 90 degrees and all four sides are congruent, we're effectively treating one side as the base and one side as the height, likewise in a rectangle. And the important point to note in the case of a parallelogram and a rhombus is that what we're going to have in the case of a parallelogram and a rhombus is we're going to have a figure which has got both pairs of opposite sides parallel, but we do not necessarily have 90-degree angles at any of the vertices, and so we can choose any of the four sides to be our base, but what we do need to do then is ensure that we are finding the height, which is an altitude, which is the distance between the pair of the bases or the pair of parallel sides. Okay, and very often, as you'll see noted on the right-hand side here, we may need to use some trigonometry, some SOHCAHTOA, special right triangles possibly, or indeed Pythagoras' theorem in order to find the height. Okay, triangle theorem is something we've worked extensively with, and this, of course, base times height over 2 applies for all triangles, equilateral, scalene, isosceles, right, etc. Okay, we have two other formulas. One is a formula for a rhombus, and as you can see above, rhombus is appearing twice. The reason we have an additional formula for rhombus is that you can use the base times height, but because of one of the characteristics of a rhombus, namely that the diagonals both bisect each other and do so at 90 degrees, we do have this alternate formula for the area of a rhombus. And so I'll very quickly explain to you how it is that it works. I'll try and draw a slightly better rhombus in this case. So we should have, in the case of a rhombus, all four sides are congruent, and what we have is diagonals which, so that's very badly drawn, but let's pretend that those diagonals intersect each other at 90 degrees. And what you can see is what we have is four right triangles. And so what we're able to do is, if you focused on just one of the right triangles and you were to find the area of this, you can see that it would be half of one of the diagonals, which we would treat as the base, multiplied by half of the other diagonal, which we would treat as the height, and then we would multiply by 1/2, so base times height over 2, which is the formula for area of a triangle, and this would give us d1 d2 over 8. And then hopefully what you can see is that that would give us the area of one of the four congruent right triangles contained within a rhombus. And so if we were to multiply by 4 and simplify that, you would get the formula d1 d2 over 2. And so for a rhombus, and of course therefore for a square, you could use the formula d1 d2 over 2, where d1 and d2 are the diagonal lengths. So this provides an alternative for us for a rhombus. And then of course the reason a square works is because a square has all of the characteristics of a rhombus, and therefore you could use that formula too. Okay, and then the last of the area formulas just to touch on, and then we'll do a quick example on one of the areas, and then move on to the focus, which is areas and volumes of right prisms specifically. Okay, so we're still dealing now with two-dimensional figures, and when we move to the prisms, we'll be dealing with three-dimensional figures. So the last possible figure that we want to look at is the trapezoid. And so if you recall by definition, a trapezoid is a quadrilateral with exactly one pair of opposite sides parallel. And so it is not a rhombus, a rectangle, a square, or a parallelogram. And so what we do have here is a very similar formula, though. You can see the characteristic of the formula. Instead of base times height over 2, we have two different length bases. And this is a very key and important point. We must use the parallel sides of the trapezoid as the bases, and that is to ensure that the height that we find, or the altitude, will remain the same no matter where we find it, because of course the distance between parallel lines remains constant. Okay, so we must use the parallel sides as the bases in the formula, and essentially this is a variation on base times height over 2, only what we have to do is add the two bases. So let's say this is base 1 and this is base 2. Essentially what we're doing is we are adding the lengths of those two bases and dividing them by 2, because we are finding the average base length, and then we are timesing by height. And so a small variation on the formula from base times height for a parallelogram to base 1 plus base 2 over 2, average base length times by height in the case of a trapezoid. Okay, so we'll do one quick example of finding an area. And so in this particular case, you can see from the markings that all we know for sure is that this is a parallelogram. And since it's a parallelogram, we've been asked to find the area. The area of a parallelogram is base times height. We can treat either of the two given sides or four given sides, because of course we know that the opposite sides of a parallelogram are congruent. We can treat either of them as bases. In this case, the quickest, most efficient method is to treat the 12 as the base. 7 is not the height. What we now need to do is to drop an altitude, and what we're going to do is find the length of what I'll call h, the height, and we will then do base times height. In order to find that, of course, we are going to use SOHCAHTOA, and so we have 47 degrees as our given. That is our opposite side, and 7 is our hypotenuse. And so that's our hypotenuse, that is our opposite side, and we're going to use the sin or sine ratio. Sine of 47 degrees is equal to opposite, which is our height, over hypotenuse, and therefore our height is going to be 7 sine 47 degrees. The area of our parallelogram, therefore, is base times 7 sine 47 degrees, which we can then approximate. And so we will say 12 multiplied by 7 multiplied by sine of 47, and we get 61.43 corrected 2 decimal places. So 61.43. Technically what we should do is say square units, because we are talking about an area and we did not have any units given. Okay, so that's a quick introduction to area, and the reason really that we need the area of our two-dimensional figures, so all of these are two-dimensional figures, is that they in turn are going to make up the bases. As you can see from the diagram over here, they're going to potentially make up the bases of our prisms. And so what we really focus on is right prisms. And so if you have a look at diagrams A and diagram B, diagram A is an example of a right prism. And what happens in a right prism is that we've got each of the edges perpendicular to the base. The figure B is known as an oblique prism, and really that is not something that we focus on in this chapter, but just so you can distinguish between the two. So if we come back up, really what we're looking at is finding, excuse me, three things. We're looking at finding volume, which is really the amount of space that the figure occupies. We're looking at finding its surface area. So that is the area of all of the surfaces that make up the figure, and that consists of two parts, our base areas and our lateral area, which is just the total area of all of the sides of the object, and then we have our bases. And this is where we needed our introduction to areas, because by definition, in the case of a prism, it is a 3D object made up of two congruent polygons in parallel planes, and those are essentially going to be our bases. And those polygons could be triangles, trapezoids, rhombuses, squares, or any one of the other figures that we've just had a quick intro on. Okay, and then typically, as you'll see from the note below, the lateral faces have what are known as lateral edges, and in the case of right prisms, those lateral edges are essentially the altitude or the height of the figure. And then if we move down, you can see, so the altitude is the perpendicular distance between the base planes, which really is height, as I referenced. And what we need to be able to do is find the area of these figures, which is going to be finding the area of the two bases. In this case, the base is a pentagon, so we would find the area of the two pentagons, which we're actually going to do next lesson, and then we would find the area of each of these, which are rectangles, and those are the lateral faces. And so in the instance of an oblique prism, the lateral faces are not all rectangles, but as I mentioned, we don't really spend any time on oblique prisms. Our focus is primarily on right prisms. Okay, so what we're going to do at this point is jump ahead, and I'm going to explain the different formulas and go through a couple of examples, and I'm going to do that in part 2 of the video.